Hello, my name's Chad Pricer,
And my name's Kelsey Chrysler.
and today we're talking Kafka aggregation. Today I'm going to walk you through the code and then show a quick JavaFX demo.
And before we do that, I'm going to show you a quick animation that I created on what the application does.
Let's imagine we are planning a party at our house. Mom has made a list of things she would like done before the party starts. Things like cut the grass, get groceries, and set up tables, chairs. She has each member of her family take a chore from the list. The fact that these chores might involve getting in a car or getting gas for the tractor isn't something that she is worried about. All she cares about is that the checklist gets updated as the chores are completed. The chore is either successfully complete, or if something goes wrong, it failed. To model this in Kafka, we can use events and aggregate them so that when a chore is complete, the checklist is updated, and when all chores are done, the entire checklist is complete. Let's take a look at how we can do this. The Kafka Streams DSL has an aggregation function. Typically, you'll see examples of this being used to count the number of clicks or calculate an average. Today, we're going to take a look at the party example where a party planner creates a list of to-do items. People go out and update the status of those items as they complete the tasks, and then update the party planner's view of the party. This example has a party planner who writes to the party topic and the party to-do items topic. They'll create a party, create a list of items, attach it to the party, assign it to the workers. The workers will read the party to-do items, and as they complete the tasks, they'll write back to the party to-do items with an updated status. The party planner's view reads the party status topic, which has the updated list of items with their current status and the status of the overall party. There's a Kafka stream microservice that creates a K-stream from the to-do items topic. It then uses the stream DSL aggregation function to create the list of to-do items with their latest statuses and writes it out to the party to-do list. The stream application also creates a K-table to K-table join from the party and the party to-do list topics, and it'll update the overall status of the party based on the status of each item in the list, and then write that out to the party status topic. The message in the end looks something like the JSON on the right here, where we have the party name, the party planner, the list of to-do items with the current statuses, and the status of the party overall. The aggregation projects consists of 4 code bases. We have the common, domain, stream, and JavaFX. The common project has the surveys in it that are used by the JavaFX and stream applications. The domain project has the Avro schema and the generated classes from that schema. When you run these projects, you're going to want Java 18, Kafka 3.2.1. The stream application right out of the box uses the writes to Redis. You don't necessarily need to do that. There's instructions in the README on how to take the Redis code out. If you don't want to mess with Redis, you don't have to. The JavaFX application won't be affected by it. It's just kind of there to show. I wanted to show how you could potentially write these updated party statuses to Redis. All the projects are built using Maven. To build and run the applications, you're going to want to build aggregation, the common first, then domain. You can build those in any order. They're not dependent on each other. And then you're going to want to build the stream application and the JavaFX application. Again, you can build those two in any order. They're not dependent on each other, but both are dependent on domain and common projects. Then you're going to want to run Kafka, Redis, the stream application, and the JavaFX client. After you do that, you can start interacting with the JavaFX client, creating parties, to-do items. You can have a second view open to update those to-do items, and you'll see the party status update in real time. Some important things to remember about this example: it does use a K-table to K-table join, and as we know, those K-tables create a RocksDB on the client side, it'll pull down the state and create those tables for each partition. So you want to make sure that, or be aware that if your topics are really huge, your startup time for these applications, at least the first time, might take a while as that state builds on the client. So you're going to want to take some time, plan out the number of partitions and the number of instances of this application that you're going to want to run based on the size of your topics. You're going to want to implement a topic retention period that's appropriate for your application. Again, you don't want these topics growing indefinitely because you are using the K-tables in the join. The optimal way to run this on Kubernetes, if you're doing it that way, you're going to want to take a look at stateful sets and static membership. So again, that you don't have to rebuild that state every time your pod restarts. Make sure that the aggregated object that you're building isn't going to get too big. Remember, you have about an 8 megabyte limit on your Kafka topics. Each message can be about 8 megabytes. So if you're going to have like millions of to-do items in your aggregated view, this particular pattern probably won't work for you. You're probably going to want to find a different way to do it. Let's take a look at the stream application, specifically the build topology method. The first thing we do is create a standard Kafka Streams Builder instance on line 128. And then on line 129 through 131, we create several surdays that allow us to serialize and deserialize our Avro objects. On line 134, we create a K-stream from the to-do items topic. And on line 136, we take that stream, we do the Kafka group by key function and the aggregate function. Note that for this example, all of the topics are keyed by party ID. The aggregate function takes several parameters. The first one is a lambda that allows us to create a new instance of a list for any key that doesn't exist on the topic. So you can see on line 137, we create an item list, and on line 139, we return it. The second lambda function allows us to do the actual aggregation. So it gives us the ID of the topic, it gives us the current item or message that's from the topic, and then a current list of those items. So on line 141, the first thing we do is just add the new to-do item to the current list. And then on line 143, we return that list of objects. We then use the toStream method to write it to the to-do items list topic. On line 147 and 148, we create our two case tables. One is from the to-do items list topic, which we wrote to on line 144, and the other is from the party topic. On line 150, we then take those two K tables and we do a left join on them. The left join allows us to read through the most recent version of the list and update the party status. We then return the party and we write to the party status topic. Finally, on line 160, we create another K-stream from the party status topic and we do a for each on it and we write that out to Redis. So that's the portion of the code that allows us to write the persisted party status object to Redis. You can take that out if you want to. It won't affect the JavaFX application. All right, so let's take a look at the running code. Okay, so the first thing I did was I started up Zookeeper, ran Kafka, and then started up the Redis server. You can get more details about how to do that on the README. And then I'm going to start up the Java Stream application. All right, so that's running. And now I'm going to fire up instance of the JavaFX application. Now this FX application is using the Atlanta FX theme or skin. So we got this nice dark look and feel to it. The first thing we do is select the user that we want to work with. I'm going to also start up a second instance of this application, and I'm going to select a different user. So over here I'm going to create a party. All right, So you can see that the party was created. There's some activity back here for Kafka, adding that to the topics. And now I'm going to create a to-do item. I'm going to assign that to my other user, Chad. That's me. And then I'm going to put it in to-do, and gonna send me out to get groceries. Alright, so now you can see that I've added, you can see that the party itself has the to-do item for Chad to go get groceries, and in my view over here we have the to-do items, we have the grocery to-do item. So as I did that, we wrote to the topics, and this one read the topic, and you can see that I have my to-do item in there. So if I want to say that I went and got groceries and I finished that task, I can mark it as done, and we see that over here the status of my item has changed to done. If I create more items, you can see that over here it's to do, and I've got it also in to do status over here. So I've created multiple items. I've assigned them to the same person, and you can see that their list updates. All this is happening via that aggregation function and k table to k table join that we did. Likewise, if we had a third instance of this app running, say that maybe same person, and they were adding, maybe Suzanne had her app running on her machine at home, and she also had her app running on a phone, and she created a to-do item down here. You can see that both views updated almost simultaneously. So we have multiple items, multiple to-do items. If we click done, we see that again these items updated correctly. As I click done, the status is updated in each view. So Kafka, of course, is working very fast here. It always works very fast, but it's extremely fast here because we're obviously running on one machine. So I hope you enjoyed the presentation. Hope you get something out of the code, and we'll see you again soon. Thanks.